So we are saying that to discuss mechanical engineering science, we need to understand a few things. So we look at applied science, but the world of science is so vast that the present day scientists and technologists have to group the various spheres of scientific activities according to some common characteristic to facilitate their training and research programs. So you'll find that under applied science, you have a branch called engineering mechanics, and this deals with the laws and principles of mechanics, along with the applications to engineering problems. So you'll find that the knowledge of engineering mechanics is very essential for an engineer in planning, designing, and construction of his various types of structures and machines. So in order to take up his job more skillfully, an engineer must pursue the study of engineering mechanics in a most systematic and scientific manner. So beginning and development of this engineering mechanics, you will be able to read through all of this, but they are people or strong pillars behind the development of engineering mechanics. And one of them is the Aristotle man. Then you'll have Archimedes, and the most important person is Sir Isaac Newton, who lived in 1643 to 1727. You'll find that much of his work is studied by engineers as they start their engineering career and even throughout their engineering practice. So let's look at the divisions of engineering mechanics. So we are saying that the divisions of engineering mechanics, we have statics, dynamics, and kinematics. So statics, these are the words that you have to understand right away from the very beginning. Statics.
Excuse me, lecturer.
Yes, please.
You left when you had just started telling us about engineering mechanics. So
yeah,
now I don't know what.
That one I didn't spend a lot of time there. I said it's just a branch of applied science that deals with the laws and principles of mechanics along with the applications to engineering problems. And I talked about the history. I said that the people behind that engineering mechanics, we can find that the very first time it was talked about was by Aristotle, and then later on we see that a number of people like Archimedes and Isaac Newton contributed a lot of work to engineering mechanics. So you will always find these guys, the Galileo Galilei, Leonardo da Vinci, all these guys have had serious work in the area of mechanics and mathematics, because mechanics and mathematics go hand in hand. And as you begin your engineering career, you should be able to understand that the contribution of these researchers and scientists. So the divisions of engineering mechanics include statics, dynamics, and kinetics. So what is statics? It is the branch of engineering mechanics which deals with the forces and their effects while acting upon the bodies that are at rest. So the word at rest is very important. So we are talking about a branch that deals with the forces and their effects while acting upon bodies that are at rest. When you look at dynamics and the kinematics, they are an opposite to statics, because we are looking at forces and their effects on bodies that are in motion. So if they are in motion, we will look at either kinetics or kinematics. So under kinetics, we will find that it is again a branch of dynamics in which bodies are in motion due to the application of forces. Now in kinematics, we don't give reference to the forces that are responsible for the motion. So you have to understand the two. Dynamics and statics are actually two opposite things. Here we are talking about bodies at rest. Here we are talking about bodies that are in motion. But again, this dynamics is divided into two. We are talking about in kinetics, a branch of dynamics. We are talking about forces. We are talking about bodies in motion due to the application of forces. So here, forces that are causing motion are considered. Whereas in kinematics, forces causing motion are not considered. Are we together?
Yes. Yes, sir.
Okay. Next is that we need to talk about the fundamental units. So the fundamental units, we will see that we have derived units and a system of units, or SI units. So the fundamental units are basically the units of length, mass, and time. These are called fundamental units: mass, length, and time. So let me write for you something here. So I have said that engineering mechanics has statics and dynamics. And dynamics is again divided into kinetics and kinematics. So here we are talking about bodies at rest. Here we are talking about bodies in motion. Bodies in motion, we mean cars, we mean water, anything, any matter. Matter is anything that occupies space. It can be air, it can be water, it can be, a liquid, it can be a solid. So if you have gas in motion, then it is in dynamics. It could be under a pressure force. If you have a vehicle moving, you have a propulsion force, okay, acting on it. So it's a solid body in motion. So there we talk about dynamics. Now, if they are in motion, here in kinetics, forces that cause motion are dealt with. Here, forces are not considered. So I could as well say that here, forces are considered. So that's what we are meaning, the difference between the two forms of engineering dynamics. So we talked about fundamental units. So these are the units from which derived units are obtained. So derived units are obtained from these ones. So the fundamental units include, can anyone give me one of the fundamental units you know? Yes?
Kilogram.
Okay. Okay, kilogram. Yes, and that is for a mass. So I want us to, okay, maybe let me say fundamental quantities. Yeah, fundamental units. We have a kilogram, that is one, and this is for mass. Then another one is a meter, isn't it? Okay, let me write in full.
The length. Meter is for the length.
Yeah. So we are saying we have a kilogram abbreviated as kg, okay? And then we have a meter abbreviated as m, and this is for the fundamental quantity called the mass. This is for length, as you have said. What else? Another one is called the second, abbreviated by S, and this is for the fundamental quantity called the time. So here we have talked about the fundamental units and we have talked about the fundamental quantities. But you will also learn, like in the electrical, actually the mechanical and electrical field. Let me first write this. We have mass, length, and time. So you'll find others like a Kelvin. This is K, and this is for temperature. Okay, and that's where some people add a K. Another one is current. So current is measured in amperes. That is A, and this is electric current. And we shall also add it here. So we could add them here as current and temperature. So you can see we have fundamental units, we have fundamental quantities. So in simple terms, if you look at this, we said that fundamental units, they are the ones that give us the derived units. In other words, you can note that fundamental units cannot be derived from other units. So that's very important to note. So we have a system of units. I've finished that. Okay, maybe you can tell me examples of derived units. Maybe if you just examples of derived units. And we said derived units are units obtained from fundamental units. Are we together?
Yes, we are together.
Okay. Now examples.
We are trying.
Okay. Examples we have like volume. Whatever you know that it has a formula, that area is equal to this, volume is equal to this, velocity is equal to this. Just tell me now, what are the examples of derived units? Okay, derived quantities. Let me say examples of derived examples of derived quantities. So I had cheated for you. Volume. Next. Just say what you know, what you remember. Okay, people don't remember. We have area, we have acceleration. Anything that you know is expressed in more than one, let me say 1 unit. Maybe it is meters cubed, it is meters squared. Now that quantity is the one I want. Acceleration is in meters squared, so this is in meters cubed. The dimensions of area is m squared. Acceleration is meters per second squared. What else? You know velocity? Velocity is
Speed.
meters, and speed, which we can take as so speed can also
We
take
have force.
yes, there is a force,
Newton.
and etc. and etc.
And pressure.
Pressure and etc. So those are fundamental quantities, and they have no. Those are derived quantities, and they have derived units. So that's very important. Then we talk about system of units. I know you remit some of these things and start asking. So let's talk about systems of units. So we have what we call MKS system. So MKS system, this is a system that is sometimes called metric. We are talking about the system that represents quantities in terms of mass, which is in kilograms, length in meters. So we are talking about meters, we are talking about kilogram and second system. So if you see units, e.g., units like meters per second, this is MKS system. It's just a system of units where you represent your units in terms of either meters and second or kilogram and second, kilogram and meters. Wherever you see those components or fundamental units existing, just know it is an MKS system. So that is one. Number two, we have what we call a CGS system. So CGS system, we are talking about a centimeter, we are talking about a gram, and a second. So mass is here, length is in centimeters, mass is in grams, and the time is in seconds. So the moment you see units like centimeters per second, grams per second, yeah, just know these are representing a CGS unit system. Are things entering? Are we together?
No.
We are not together. Why? I said MKS. We are talking about systems of units. And MKS system of unit or MKS unit system, it has meters, has a kilogram and second. So wherever you see units like meters per second, you see units like kilogram per second, you see kilogram per cubic meter, we are talking about MKS unit system. Where you see something like grams per second, you're seeing grams per cubic centimeter, for example, for density. You have grams per cubic centimeter. Here we are talking about a CGS unit system. So in other words, it has a centimeter existing, you see a gram there, and in other units you can see a second with a gram, you can see a gram with a centimeter, something like that. That's what I'm trying to say. That becomes a CGS unit system. Are we together? Are we together? Yes?
Yes, we are okay.
Good. So, we have also what we call FPS. But FPS, we are now talking about feet, pounds, and seconds. So let me write here. The third one is FPS unit system. So here we are talking about feet, we are talking about pounds, we are talking about seconds. So this is length, this is mass, this is time. So e.g., if you see something like pounds per second, you see something like feet per second, this is feet per second, this is pounds per second. So the moment you see something like that, this one is called Imperial British Pound. So IB or LB, sometimes you always find in those old textbooks, they have these units. So that means a pound. So it's a pound. If it is stroked with S, that is a pound per second. FT per S per second, that is feet per second, as you can see here. So these are from an FPS unit system. Then we also have SI units. So these are just standard and these have been standardized from international communities. And so you know that if I measure a mass today, if I measure a mass here in Uganda, it is equivalent to 1,000. 1 kilogram mass is equivalent to 1,000 grams. Okay? Those are standards. If I measure 100 centimeters, it is equivalent to 1 meter. Whether I go to Britain, whether I go to India, whether I go to South Africa, it is the same. And this is basically important to ensure that there are no confusions in measurements. Because if South Africa uses their own measurements, Uganda uses their own measurements, in any dealing, you'll find that one either cheats the other or you find them fighting. And therefore, to avoid all those conflicts and issues, standards are on board to make sure that no one is cheated in case there are transactions. Are we together? Yes?
Yes.
So for that matter, we have what we call those SI units, and I've said they are standard. And for density, it is in kilogram per cubic meter. Okay? Let's see. Force is in newtons. We are just talking about SI units that you already know. Power is power, and this is in joules per second or watts. Pressure is in Newton per square millimeter, but you always take Newton per square meter. Anything that is outside this, you always have to do a conversion. And we know that 1 meter is equivalent to 100 centimeters. Okay? 1 kilometer is equivalent to what? 1,000 meters. So we always remember all of these figures by this kind of abbreviation. So you can always see you have 1, 0, 0, 0, 0, 0, 0. So meaning in one, if this is length units, if we talk about length, for example, in one, let me see, in one kilometer, you are going to always have 1,000. You always have 1,000 meters. I just come here, press a 1. How many zeros? So this is a kilometer, hectometer, decameter. This is a meter, decimeter, centimeter, and this is a millimeter. Okay? So 1 kilometer has how many millimeters? 1 million millimeters. Let me say, okay, let me write it here. So 1 kilometer is equal to 10 to the power 6 millimeters. Meaning, still 1 kilometer is equivalent to 10 to the power 3 meters, according to this that I have here. So for the people in Kabale would say, Kampala, Hariyo, dance, makeke, don't care, madam. I think ISCJ will help you maybe translate it and put it in your own language. But I believe in every corner of Uganda, they have how they can translate this. But this is a kilometer, hectometer, decameter. This is a meter, decimeter, centimeter, and millimeter. So if I want 1 kilometer in terms of a decameter, then I would say this is 1, 0, 0, 0, 0. So that would be 10,000 watt decameter. Something like that. This is a decameter. So let us just basically talk about values in terms of if they give us SI units, everywhere you hear a kilo means 1,000. So if it is 1,000, if they tell you we are talking about 1 kilojoule, so this means this has 1,000 joules. If we talk about 1 kilometer, this is 1,000 meters. If they talk about 1 kiloliter, this is 1,000 liters. And so on and so forth. So I've finished all of this. You'll just look through. So our next area we have to look at is called composition and resolution of forces. This other part is just giving you the general math that you have to understand, and we are not here to learn math. So, and the rest of the things I've been telling you, they are the things you already know. So the real work starts from here. Composition and resolution of forces. So we need to define what a force is. So a force is a very important factor in the field of mechanics, and you can define it as an agent which produces or tends to produce or destroy or tends to destroy motion. Okay? So it is an agent which tends to produce or destroy motion. That is a force. And then we can talk about effects of a force. So here we shall talk about and effects effects of a force. So a force may produce the following effects on a body, okay, or in a body on which it acts. It may change the motion of a body. It may retard the motion of a body. It may retard the forces already acting on a body, thus bringing it to rest or equilibrium. It may give rise to internal stresses in the body. So someone can ask you, what are the likely effects of a force? Obviously, nobody will ask you a question like this. From today and onwards, just know we are going to be dealing with scenario-based questions. So this is a new curriculum that emphasizes setting of scenarios. So someone can set a scenario and you find that he is asking this question indirectly. Okay? So if you find that they are talking about effects of the force that was applied to a body, okay, one of the things that you have to remember is that it may change the motion of that body. This is how a scenario can be. Someone can say, Amos set a block on top of a table in motion, and his friend applied a force on it. What are the likely effects of the force which a friend to Amos applied on a body? So there is nothing like you have to think about answers from Mars. They are the very answers here. So the force the friend applied could change the motion of the body, it could retard the body or retard the motion of the body. Retarding means you are, if a body is accelerating and you retard it, that means you're moving against its acceleration. You're applying like a brake. So if you apply like a brake, it might, if the brakes are, if the friction is not too much to stop the body may still keep in motion. But as long as you keep this force to retard the body, a time may reach when this body can no longer move. It will just have to stop. So we are talking about applying like brakes or a braking force. So it may retard the forces already acting on a body, thus bringing it to rest or in equilibrium. You know, there are some forces that act to oppose motion of a body. For example, friction. So if the body is already experiencing friction and you apply another force that is opposing its motion, then you can bring it to rest. It may give rise to internal stresses. For example, you could push a force and you somehow change its shape. So this can result into stresses within the body. Let's talk about characteristics of a force. Yeah, this is very important. Characteristics of a force. The force has magnitude. So magnitude, we are talking about e.g. 20 newtons, 10 newtons or kilonewtons, etc. A force has direction because it is a vector quantity. Are we together? Is Danish still available or he already exited?
I'm here listening.
So are you picking something, especially the characteristics of a force?
Yes, sir. I'm getting.
Yeah, a force has a magnitude. So in any case, if you indicate a force on a body, you are supposed to show its magnitude. You're supposed to show its direction. You're supposed to Yeah, in most cases, those two things, those two characteristics are on each and every force. Then in other times, you can show the nature of the force. It can be a push or a pull. Yeah, which you can show by pressing an arrow on the force. You can also indicate the point at which the force acts on the body. So let's say nature has a nature, either a push or a pull, indicated by the arrowhead. Then we are saying that a force has a point of action on the body. So, e.g., a force acting on a block let us assume that is our block in 2 dimensions. This may be on surface like a table. So if a force is like this, then this is going to be a push because the direction of the arrowhead is pointing towards the body. And we can see that it is moving from east to west. That is the direction of the force. And at this point, that is the point of application of that force. If this force is like this, maybe this is force F1, this is force F2, and it's acting here. So this is a pull. And it is also in that direction. And it is having a point of application. The magnitude of this force is F2. The magnitude of this force is F1. Let me say this is F2 newtons. F1 newtons. So that means that it has a magnitude. So we will also talk about the principle of transmissibility of forces. The principle of transmissibility of forces. The principle of transmissibility of forces states that if a force acts at any point on a rigged body, it may be considered to act at another point on its line of action, provided the point is rigidly connected to the body. So this is what we mean here. If you have a body like this, and you happen to have a force acting here, the principle of transmissibility tells us that we can prolong along the line of action of this force to this point, as long as we don't change the direction of this force, and the line of action, then this force remains the same as this. So if this was F1, then we would just bring it outside here and it becomes F1. So maintain the direction and the line of action. That's what the principle of transmissibility tells us, and we shall be using it in a number of areas as we go along in this mechanics. Then the system of forces. System of forces. We have the fact that you have two or more forces acting on a body, it becomes a system of forces. If we have two or more forces acting on a body, it becomes a system of forces. And the following are important from the subject point of view. We have coplanar forces. So we have system of forces. Means we have two or more forces acting on a body. So one, we are looking at coplanar forces. So coplanar forces are forces that are acting on the same plane. So the lines of action of these forces are on the same plane. Collinear, the lines of action lie on the same line. So here, lines of action are on the same plane. A line of action. Do you still remember what a line of action is? If I apply a force here, for example, this F1, we said its line of action is along here, through the force itself and throughout the body. Anywhere along, as long as you draw a horizontal line or any line that points in the direction of the force to and from where the force is, then you're talking about the line of action, but it is always imaginary. So that's why we can give it in a dotted form. So we could have a plane like this. We will be talking about planes. This is the y-x plane. So this is the xy plane. Now, assume that you have a force. You have a number of forces, okay? For example, here, you have this, you have that, you have that. So you see that the lines of action of these forces are all lying on the xy plane. So maybe this is F1, this is F2, this is F3, this is F4. So these are coplanar forces. You can also have the z-x plane. Maybe this is the direction is z, and this is the x direction. So this is the XZ plane. Now, if you have forces also acting here, like this, remember it's parallel to X, and maybe it's parallel to Z, maybe it's again parallel to X. So you have the lines of action of these forces. Maybe this is F1, this is F2, maybe this is F3. This is coplanar forces. So lines of action, the lines of action of these forces are on the same plane. Now let's go to collinear. Now collinear forces are forces whose lines of action lie on the same. So meaning you have different forces acting on the body like this. This is a force, maybe F1. This no. This is a force F2. This is a force F3. So you can see they are along the same line. Their lines of action are along the same line. So if they are along the same line, we say these are collinear forces. Now, concurrent forces are those forces which meet at one point, okay? You can have coplanar concurrent, they are in the same plane and they meet at one point. You have coplanar non-concurrent, they are in the same plane but they do not meet. For example, these ones here, F1, F3, F1, this was supposed to be like this. Yeah, F1, F2, F3, these are coplanar, but they are non-collinear. And they are also non-concurrent. So we say the concurrent, we have to meet at one point. Coplanar concurrent, they are in the same plane and they meet at one point. Coplanar non-concurrent, it means they are in the same plane and they do not meet at one point. Non-coplanar concurrent, they are not in the same plane but they meet at one point. Non-coplanar non-concurrent, they are not in the same plane and neither are they meeting at one point. So you have to also understand that. Let's look at the resultant, then we look at the composition, and then we shall stop at the parallelogram law of forces. So resultant force is a force that produces a same effect as if you had brought a number of forces together. If you have 10 forces acting on a body, their effect is the same as the effect produced by their resultant force. So let's talk about resultant force. So I'm saying is a force with the same effect as a group of individual forces working together. So e.g., you could say I have a body, okay, with these forces. Now let me first consider one direction for simplicity. So you have 10 newtons, you have 5 newtons, and here you have 20 newtons. So resultant will be, I just get the sum of the the highest the highest sum, or the highest force minus the smallest force. So here this will be 20 minus 15, and that would be 5 newtons. So if I applied 5 newtons to this body, so resultant force is equal to 5 newtons. Meaning, if 5 newtons force was applied, it would have same effect as using 15, as using 5, 10, and 20. Using 5 newtons, 10 newtons, and 20 newtons at the same time as above. If the directions change, then the resultant would change. So that's what we mean by a resultant. If they were like this, maybe this is 15 newtons, kilonewtons, maybe this is 30 kilonewtons. The resultant here would be 30 minus 15, giving us 15 kilonewtons. So it means if I apply a force of 15 kilonewtons on this same body in the same direction as where these two forces are acting, it would produce the same effect as if I had these two forces acting on the same body at the same time. So you have to understand what a resultant means. Composition means the process of finding out the resultant force. Yeah, that is called composition. So all that we have been doing is called composition. In the process, composition is the process of finding out the resultant of a number of given forces. Methods for resultant force, we will find that we have an analytical method where we talk about calculations. We do calculations here. Then method of resolution is also there. I mean, calculation here, in analytical method, we use a formula. Then here, we follow a given method called resolution. You resolve forces vertically and horizontally. Then we look at the parallelogram law of forces. So under analytical method, we use parallelogram law of forces, and somehow, somewhere, we also use the method of resolution. Let me put so the parallelogram law of forces says that if two forces are acting simultaneously on a particle, and they are represented in magnitude and direction by the two adjacent sides of a parallelogram, the resultant may be represented in magnitude and direction by the diagonal of the parallelogram, which passes through their point of intersection. And mathematically, the resultant force would be like this. This is what you would have. So the resultant force Rf would be the square root of R1 squared plus R2 squared plus 2R1 R2 cos theta, whereby theta is the angle in between the two forces. So we can say that if we have forces F1 and F2, then theta is the angle between the two forces, and alpha is the angle with which the resultant force makes with one of the forces. So that you have two forces, for example, we are saying maybe this is R1 and this is R2. So the result is going to be represented by the diagonal. So if we talk about the diagonal of a parallelogram, then you just have to imagine that this was a parallelogram and then complete it like that. So this is this angle here is what we are calling theta, and alpha, this is RF. Alpha is the angle with which the resultant force makes with any of the forces. So theta is the angle between the forces, maybe R1 and R2. Alpha is the angle with which the resultant makes with any of the forces. And this is how we get. So if you have the F1, if you have F1 plus F2 cos theta being at the bottom, that means this resultant makes an angle alpha with F1. But if you F2, if F1 is on top and you have F2 down here, okay, then that means the resultant makes an angle alpha with F2. So let me maybe make that one clear. So if RF makes an angle alpha with R1, then tan alpha is equal to F2 sine theta divided by F1 plus F2 cos theta. Now, if RF, or the resultant force, makes an angle alpha with R2, then tan alpha is equal to F1 sine theta divided by F2 plus F1 cos theta. So that one can be proven, but for purposes of simplicity, we shall leave it at that. Now we want to look at an example so that we leave here when we have at least calculated one example. So we are told that two forces, 100 newtons and 150 newtons, are acting simultaneously at a point. What is the resultant of these two forces if the angle between them is 45? So what would that mean? Solution. So we said that the resultant force using the parallelogram law of forces is equal to the square root of R1 squared plus R2 squared plus 2 R1 R2 cosine the angle in between them. So that means the resultant force would be square root of 100 squared plus 150 squared plus 2 times 100 times 150 cosine of 45. So from there, you evaluate this and get the answer. So the answer is 232 newtons. Let's look at another example. Two forces act at an angle of 120 degrees. The bigger force is of 40 newtons, and the resultant is perpendicular to the smaller one. Find the smaller one. So we have started the real mechanics. Okay, it's not yet the real, but at least we are trying to have a feel. So we are saying, according to the method we have looked at, is the parallelogram. And the parallelogram, you're supposed to have a longer side and a shorter side, because the parallelogram is like this. You have a shorter side and you have maybe the diagonal, then you'll have a longer side like this, and the other side opposite. So they always tell you that these two are equal, these two are equal, and this is the resultant. So this is a smaller, this is a bigger side. So you have been given the magnitude of the force on the bigger side or on the larger or longer face. So that means we can draw our parallelogram and let's give a shorter side and a longer side. So this is going to be the resultant. So we are told that the resultant an angle of 90 degrees with a smaller one. So we are going to call it X. And this is, remember, this is 40 Newton. So if it makes an angle of 90 here, okay, so what is going to be this other angle? Remember, we are told that this is 120 degrees. So if this is 90, then what remains down here is 30 degrees. So 90 plus 30 is equal to 120 degrees. So we are told to find the smaller force. So if we want, we can use that parallelogram law Okay, and then okay, we need first find the resultant. So this is the resultant. Now we know that tan alpha is equal to for example, F1 sine theta divided by F2. Okay, let me use R1 and R2. So I'm saying tan alpha from tan alpha is equal to R2 sine theta divided by R1 plus R2 cos theta. So that means we are talking about the angle between the resultant force and R1. You can see what we have up here. If it makes an angle alpha with R2, then we would have R2 here. Let us make this R and this R. This is R2 sine theta, R1 plus R2 cos theta. Yeah. So that means with R1, let's confirm something here. So if it is with F2, then you have F2 at the bottom here and has no trigonometric ratio. If it is with R1 or F1, then it would be F1 without anything here. So if it is R2, then this is how it would look like. So we need to rectify this. So this would be R2, this would be R1. If it's R1, if it makes an angle with R1, then we would have R2 here, R2 here, and R1. So if it makes an angle, let me assume this is R1 and this is R2. So we're talking about the angle it has with this known force. We have to work with what is known. So here, what is known is 30 degrees and 40. So if R2 is 40, then we can change something here. This becomes R1, this is R2, and this is R1. So here, theta will be 30 degrees, because we're talking about the angle between the resultant force and the other side of the parallelogram, either short or long. you have to just interpret it from here. Then the other force known is R2, which is 40 newtons. So from there, we will just take tan of 30, which will be R1, which is not known, sine 30, sine, this is supposed to be theta, that is theta, that is alpha. So this is supposed to be alpha. So alpha is 30 degrees and theta is 120 degrees. Because it is the angle between the two forces, that is theta. The angle between the resultant and one of the forces is alpha. So we are given tan 30, R1 is not known, then sine 90, divided by R2, which is 40, plus R1 cos 90. So this is 0. This is 1. So meaning R1 out of 40 is equal to tan 30, because we are saying this is going and this is becoming 1. So let's create more space. So here I just cross multiply and have my R1 equal to 40 tan 30. So yeah. So this person, I think they made a mistake here because the angle between the two forces here. No mistake here. This is supposed to be what? This is supposed to be, sorry, we are the ones making a mistake here. So what is theta? Theta, we said it's 120, so we just substitute in here. So what is sine 120? Sine 120 is the same as sine 120 is the same as cos 60. And this is the same as a half. Cos 120 is the same as negative sine 60. And this is negative root 3 out of 2. So we can substitute in those values. These values are known as a constant. If you have your calculator, type there cos 60. Let me see, I had my calculator here. Okay, so I want to take a cosine of 120. What is the answer? So I get cosine. So that is negative 0.5. Let's see. This should be sine 120 is supposed to be cos 60. Let's check on our table here. We can use you can please type on a calculator and we stop wasting time. Maybe someone can tell me. So if this is 120, okay. So if I have 60 here, so for a sine, this is the same as 60. So it's the same as if I'm taking a cosine of 60. So let's come back here and say 120 and we take a sine. So that is 0.86, okay, which is the same as sine 60. So sine 120 is root 3 out of 2. This is the same as 0.86. Then cos 120 is the same as negative sine 30. And that is a half or 0.5. This is the same as cosine 30. And cosine 30 is the same as. So you can plug in those values. You'll have tan 30, which is equal to R1 we don't know. R1 times root 3 out of 2 divided by 40 plus negative a half times R1. Finally, what is the value of R1? So that value is going to be 20. When you evaluate R1, you should get 20 newtons. So that is how we can deal with this problem using parallelogram law of forces and the formula that we stated here, tan alpha. But this could be a little bit uneasy for now, but as time goes by, I believe you will understand.